Hello and very welcome back to this latest video, and I just want to quickly thank new subscribers for joining in, and we've had plenty of views and plenty of subscribers, and just want to thank you for your comments. Keep those coming, it's always welcome. So very good, and well, let's talk about this next video right now, but thanks again for tuning in. So I was going through my junk box the other day, come across this interesting device here. Now you may have seen one of these before. Maybe you haven't seen one of these before. It's basically a magnetic core storage device. This is normally just referred to as a core storage plane or core storage device. I found this in the junk box the other day and I thought, never actually wired one of these up or tried to access one before. So this is pretty new to me as well. So let's let's go along this journey together here. So read up on the internet a bit about them, and you know, I've heard about them and I'm quite aware of them, but never actually tried to experiment with one or put any signals through it or try to read anything. It's basically a memory unit for storing computer data, binary data, and inside of here you have memory cores, lots of little ferrite beads, really interesting devices, and some copper wire in there crossing through, giving like cross points, bringing it out to connections on the edges here. So I'll just flip it over, and it's pretty much, you can see all the way through, it's transparent. This is actually inside of a plastic case, this particular one. Sometimes they're in cases, sometimes they're not. This one's in a safety case just to stop it from being damaged. But inside, basically what you have is ferrite beads, or very small ferrite cores. Each one of these little black dots is a ferrite core, a ferrite bead. I thought, wouldn't this be fantastic? Wouldn't this be fun if we could get this thing to actually work? Now these things are from the 60s, possibly into the 70s, and they were used a lot in early computer designs. Completely obsolete these days, totally taken over by semiconductor technology. But I thought, well, you know, we're all about having fun with electronics on here, so why don't we try and do some experiments and see if we can actually get this thing to work. And that's going to be the aim of this video. Let's see if we can get this thing to memorize some digits, or we may just start off with a very simple experiment of getting just one of these single bits to flip state, to set it to a 1, set it to a 0. Let's start small, just with one bit, and take it from there. Anyway, there you go. Memory core storage. Magnetic core storage, or just core storage as it's sometimes just referred to, is an old technique that was used probably from the 60s into the 70s sort of era, and it sort of phased out by the time it got to 1980. I think it was finished. A very early sort of system that computers used to store binary data. Binary, we know, is either a 1 or it's a 0. In a series of bits to form bytes or words. Each bit had to be somehow stored in a memory, so in order for the computer to memorize data, and it was able to store data using magnetism in ferrite cores. Now a ferrite core, here's one here, not used as part of a memory here. It's used for radio RF purposes, and this particular one is made out of ferrite, and it's about 1 centimeter in diameter, something like that. Now technically you can flip this into a 0 or into a 1 state by passing a current through the hole there in the center in one direction or in the other. And if you've got enough current flowing through the center conductor or wire, imagine this is a conductor going through there, imagine that, and you put current through this connection, through this wire here, it would flip the state of the magnetism of the ferrite core into either a 1 or into a 0 state. And that's basically a simple way of explaining how core storage works. Without getting into the analog circuitry of how you do that, that's basically how the principle works. And you can read back the data later from the ferrite bead by passing the current through again. And if you pass the current through again and you get a response from that current then you know that it was in the other state. So in other words, what I'm saying is, if this ferrite core was set to a bit of 1, and you put a current through it and you get a response back, you know that it was actually set to either a 1 or a 0, depending on the response. Now what I mean by that is, let's see, we've got our ferrite core here, which I'll try and draw. I'm not very good at drawing, and I'll put the hole in the middle. Right, so let's just assume this is our little core with a kind of 3D look through the middle of it there. And, well, what you've got basically is a wire going through, a copper wire going through the core and coming out the other side. Okay, it's usually, and it's copper wire normally. If you pass a current through the wire, it will flip the state, if it'll magnetize the core either into a 1 or a 0. That happens only when you've got enough current. There is a property of ferrite which is it will only flip state when you've got enough current flowing through, or enough magnetic flux to actually flip it into a magnetic state. If you don't have enough current, then it doesn't. It alters the magnetism, but then as soon as you release the current, it flips back again. So basically, what I'm saying is you have to have enough current to, and that's important for core storage to work. You have to have enough current to be able to flip the magnetic state and magnetize the actual core into either a 1, or demagnetize it in the other way into a 0. And it depends on which way the current is flowing. For argument's sake, if you said the current was flowing that way, turned it into a 1, then if you reverse the current of that wire and you fed it back the other way, same amount of current, just the opposite polarity, it would turn it to a 0. Now, in order to actually read whether you've programmed the core into a 1 state or into a 0 state, in other words, you know, you've reversed the polarity one way or the other, you need to be able to detect or read back the data. Once you've magnetized it, you have to be able to read the data back. So in order to be able to read the data back, you have another wire which goes through the core. Okay, and I'll just try and draw that here, like that. Another wire coming through, and this wire is what we call the sense wire. Okay, so the sense wire is basically detecting the any change from the state of the magnetic core, depending on the current, or the drive current if you like, that we're putting through it. What I mean by that is, let's suppose put the current in this direction, we magnetize the core, there's enough current there to flip its state and it becomes magnetized. We can class that as, say, a level bit of 1. Okay, that's in that direction. Now when you actually flip the state of the current and you try and read it back, you put the current this way, in other words, you're actually going to turn it to a bit 0. But in the process of turning it to a bit 0, you're also detecting with the sense wire whether the core was magnetized to a 1 or not, because it's going to have a reactive result to what you've just done. By flipping the state back from a 1 to a 0, you're going to see that as a current induced in the sense wire. So the sense wire in effect is our read connection, if you like, our read wire, our read sensor, and it's going to tell us whether the previous state of the core. Okay, so if we take it to a 1 and we've got a sense signal, it means that it was previously set to a 0. If we flip it from a 0 to a 1 and it was already set to 1, then you won't get any sense current induced in the sense wire, because it's already in the 1 state. So it's telling you what the previous state of magnetism of the core is, and that's basically the entire principle of how magnetic core storage works. So this is write, if you like, and this is read, but it's a destructive read, because every time you read from the core, you have to flip the state to see what previous state it was in. Let's consider what happens when you've got more than one core, and there's not much point in having a single core memory that would just give you 1 bit of information. That's not much use. So obviously you want to take that further and produce more bits, which would then give you like whole bytes or whole words worth of information. So let's consider what would happen if you had 4 cores, or ferrite rings, if you like, ferrite cores. I mean, you could have, say, a wire here with its own sense, and then another wire through this one with its sense, and a wire through that one with its sense, and so on. Every core could have its own wire and its own sense. But once you start to scale this up and you have many cores, the complexity of the interconnecting wires just gets quite ridiculous. You couldn't really do it for anything more than, say, 100 or 50, even 50 cores. It would just get overwhelming with the amount of parallel connections you would have going to all of those cores. So the obvious thing is to try and arrange these as a matrix. Okay, so now what we can see is, if we wanted to address any one of these cores, or bits, if you like, rather than having a single wire for every single core, put them into into a matrix arrangement. So you'd have, say, a wire here that would go through that core, then it would go through that core, and then it would come out the other end. Okay, then you have another wire here, goes through the core, and then goes through that core, and then you got a wire that coming out that way. Okay, so now we can at least address whether it's these two or whether it's these two that we want to write to. Okay, so that narrows it down a bit, but of course it's a matrix and we need to be able to get down to a single bit. So obviously you need bits of matrix. We need to go the other way as well. So this one will come through here, say, come through here, come out the bottom. Then you have another wire coming through, comes through here, and comes out the bottom. So now we're able to access individual cores. If you put a current, say, through this wire here, and you put a current through, say, this wire here, you will only be producing enough magnetism from those wires to magnetize this bit. If you half the current that it takes to flip the state of each core, if you half that, then a single current induced in one wire won't be enough to turn those two on, because you haven't gone over the hysteresis point and flipped the state of the core. That's the point. So by using half the current in one of the axes of the matrix, and you use the other half of the current to make up for the half you've removed there, then those two currents add up and gives you the amount of magnetic flux within the core to flip the state of that core. None of the others are affected because they're only half currents. So you need both X and Y to actually flip the state of the bit. And essentially this is how magnetic core storage was built. That's good, because it means now we can access or program, if you want to say that, write to, it's all valid, any of the cores. And in fact you could scale this right up, and you could have like 100 that way and you could have 100 that way. And just by selecting the matrix of X and Y wires, these copper wires that thread, they literally thread through the rings, you can program each one individually. Now, in order to read the data back, we need our sense wire, and the sense wire that we mentioned earlier is kind of like the read wire. It's a pickup wire, and it's looking for reactions, which tells us the previous state of the core. Now, so we'll take our sense wire, and this isn't easy to draw, but basically it threads through every single core in the entire matrix. It goes through all of them. So this is our sense wire coming in here, and see, I've made a mistake straight away. So it kind of comes through here, and then it goes through this one, and then it feeds from there, and it goes through that one, and then it comes through, and it comes through that one, and then it comes all the way back again like a loop. Okay, and them's your two terminals for your sense. So I'm sorry about the drawing skills, but I think you get the picture. It's basically a continuous loop of wire which goes, it threads through all of the cores, and then it comes all the way back again, so you end up with a big loop. Now that's the read sense wire. Again, it's just a copper wire, and that's looking for the reaction that you get. So when you come to program this core, let's say it was a 0, but you've programmed it by putting both of these half currents through these wires to flip the state of this core to a 1. So this core is now a 1, but in the process of flipping the state from 0 to 1, it's induced a signal into the sense wire, a voltage delivered across these terminals here, and that tells us that the previous state was a 1, because we've got one either from 1 to 0, or we've got from 0 to 1, and it's telling us the previous state. If the state's the same, then you know, let's say it's 1 and we're trying to program it as a 1, then the state's the same and you won't get any voltage produced across the sense wires here. So That's writing by putting current through the matrix wires, and reading by looking at the sense. Now don't forget, it's a destructive read, so every time you read you've got to actually flip the state, or try to flip the state of the core, and by doing that you flip the state of whatever it was previously. We measure that coming through the sense wire, and basically I think you get the idea of how the whole thing works. There is another layer of complexity to this which come out where you actually have an inhibit wire, which is basically another sense connection, which a sense wire which goes through everything, and that's to stop things being programmed. And all that's for, which we're not going to go into here because we don't need it, but all that's for is to if you layer these as a stack, you put them on top of each other like a three-dimensional cube of construction. It means using the inhibit wire you can turn off the layers that you're not trying to program. So it's like it disables them, if you like, so you can't actually write. You don't write to all of the layers, and it means you can have all of the matrix connections connected together. So there's like practical advantages to having an inhibit wire as well as a sense wire. But that's going a little bit further. We don't really need that for this. So what we're looking at here is basically core storage using write and read connections. What we're talking about here is magnetic core storage is now completely obsolete and has been for a long time. In the 80s, when semiconductor technology became a lot more accessible, they were able to replace all of this technology using integrated circuits, so they were able to produce RAMs and ROMs, and using semiconductor technology, which was much smaller than what they could achieve here with a much higher component density, and basically this just all became completely obsolete. And also the access times weren't fantastic. You were lucky if you could get an access time with clocks of like 1 megahertz. So the clock speeds for the computers that they were using had to be low in order to to cater for the access time of the core storage. And when semiconductors came along, well, of course it was just way faster, and the access times were much higher, and again the component density was way higher as well, so you could have much more memory in the physical space it took to build one of these devices. But historically they are still, in my opinion, very interesting devices, and that's the point of what we're trying to do here in this video, is to see if we can get this unit to actually work, or at least I think what we're going to try and do is get maybe a few of these bits to work. Maybe not the whole thing, because that's going to take quite a lot of circuitry, but for the purposes of just seeing if we can actually flip the state of some of these bits, maybe it's a whole 8-bit byte or something, and produce a character or something like that. So we'll see how far we get, but the purpose of the video is to build a circuit and see if we can interface with this. It'll be using, obviously, new technology to talk to this. We'll have a computer through a USB connection or something, through a serial connection. I don't actually know exactly how we're going to do this at this point. I've got some ideas how we could do this, but possibly use an Arduino microcontroller or a PIC, and we can use that to address the lines and what have you, and some other analog circuitry to supply current, to program the cores, and also a sensing amplifier. We're going to need amplify the signal that we get from the sense wire, which is a very low signal. I've been reading online, and it's typically around about 50 millivolts. That's what I've read without measuring it on the scope, but I do believe that's the sort of signals that we could be seeing from the sense wire. Maybe a little bit less, I don't know. I think it depends on the size of the core, the physical size of the cores themselves. So we're going to need an amplifier to boost the signal from the sense wire, and we're going to need current control to send through the matrix X and Y wires to flip the states of the cores. Now, one thing I haven't mentioned about these things, they have a very good advantage if you think about it, because with this being a magnetic store, it's non-volatile. So when you turn off the power, that's what we mean by non-volatile, you turn off the power supply, it retains the data. So when you come to switch the machine back on again anytime later, then all of the data that you've programmed is still there. that's excellent compared to, say, a semiconductor RAM chip, where obviously it's classed as volatile. So if you turn off the power, it forgets everything, and everything goes into a random state. It doesn't actually retain any of the data that you put in there originally. So these days we use EEPROM, which is electrically erasable PROM, and basically that means you can program it, and it is non-volatile. But that's all quite recent technology in the last sort of 10 to 20 years. So, at the time, this was excellent, if you think about it, because you could use it like a ROM. You could actually program it, switch it off, switch it back on, and all the data was still there. And that came in very useful for a certain amount of applications. It was a useful aspect of core storage, but not the primary reason for core storage. And of course, they used core storage to get man to the moon back in 1969 when the Apollo 11 went up. I mean, they had core storage in the flight computer system to save all of the variables for the mathematics that they were doing in order to get the lander to land on the surface of the moon. So as you can appreciate, this was a very useful technology for its time. So some time ago, probably 1988, 1989, something like that maybe, my first introduction to core storage went down a local second-hand shop, and we found an old programmable calculator made by Casio. This calculator at the time was pretty much unknown to the shopkeeper himself. He didn't know what it was. It had buttons and Nixie tubes on the front, but he didn't really know what it was. Maybe he thought it was a calculator of sorts, but he didn't really know what was inside or anything like that. And we managed to pick it up for about £10. And I remember thinking, there's going to be something really interesting inside of here. So so we got the thing home, we tried it, and it actually worked when we first got it. It was in working condition. Anyway, of course, we had to have a look inside. And when we took the lid off, incredibly, it was just crammed with PCBs, all with transistors, diodes, resistors. No integrated circuits that I could see, just completely done with discrete logic. And at the very back of the calculator, the very back board, we pulled that one out, and on the board, lo and behold, was a core storage device. Now, the calculator model was an AL-1000 by Casio, and unfortunately I don't have it anymore. Quite some years ago it developed a few problems. I seem to remember we actually fixed it a couple of times, but it kept going off again. So we kept finding dead transistors, replacing them and getting the thing going again. But after a while it got to the point where we just didn't really know what to do with it, and had a bit of play with it and everything. And but back then the internet was very in fact, there wasn't any internet really to speak of, and it was very difficult to find things like schematic diagrams. So we didn't have a schematic diagram for it. I was able to just repair it just by looking at it. It got a bit deep, and it got a bit time consuming to keep fixing it all the time. And eventually I think I sold it at a radio ham rally or something. Probably got back what I paid for it. So yeah, but kind of kicking myself now, because it would have been fabulous to still have that, especially for this video. However, and this is why I'm talking about this, we need to design a drive circuit and also a sensing amplifier in order for our test to work, in order to access our device. Now, I seem to remember the whole thing was done with transistors in the AL-1000, and I think we can do a little bit better than that these days. So we're probably going to end up using some chips, some H driver chips, to drive the core storage lines. But the sense amplifier was done quite easily, just with a couple of transistors and a small transformer. What I've gone ahead and done here is, by looking at the original schematic for the AL-1000, I've entered into Symetrix, which is an electronic circuit simulator, and I've entered the circuit in basically to show how it works. So this is basically exactly how it was designed in the AL-1000 in the Casio programmable calculator. But what I've done is I've entered it into Symetrix here so we can take a look at it. So I'll just quickly go through how the sense amplifier works, because this is something that we want to build. We'll have a transformer here, which is basically a one-to-one transformer with a center tap. So you've got 10 turns primary, 10 turns secondary on the top, and 10 turns secondary on the bottom. This gives us a balanced input, and what I'm doing here is I'm just simulating the pulse that would come from the sense wire. I've got a little pulse generator set up here. That's what all these little numbers are for here. So we're basically putting in a plus minus 50 millivolt signal from the generator, and that's going into the primary, and that basically replicates the signal from the core storage sense wire. On the secondary, you'll notice there's a few things here. A couple of transistors, a couple of NPN general purpose transistors. These are detecting either the positive or the negative going pulse from the output of the transformer, and are being switched on accordingly. So if there was a positive pulse, that would switch on the this top transistor here, Q1. If it was a negative going pulse, it would switch on the bottom transistor. These transistors are biased using the little bias arrangement down here to put them very close to the point where they're ready to conduct. That gets them really close to the conduction point by putting 0.6 on the base of the two transistors. And that 0.6 comes from this diode here, D1, which is forward biased, which gives roughly around about 0.6 across it. And there's a 10k pull up here to get some current flowing through the diode. The bias voltage 0.6 goes to the center tap of the transformer, so the DC condition of that goes straight through the coil and biases the two transistors, ready to be switched on if there's a pulse. Now if you remember, we actually need to be able to detect positive and negative going pulses to give the same logic output. So what's happening here, the collectors of these two transistors, remember one's detecting positive, one's detecting negative pulses. We've got a little logic AND followed by a NOT gate here, which is the AND gate is basically these two diodes here and this 15k pull-up. If these two transistors are off, in other words there's no pulse, there's no current flowing through these diodes here, the default state will be a logic high at this point. So that logic high, so that's basically an AND gate. Any zero on either of these, in other words they go to ground, any zero logic level on here will cause a zero through here and turn the output to a zero. So any zero will give a zero. It's only when they're both high you will get a high output here. And then finally on the end we'll have this little NOT, or inverter if you want to call it that. It's just a little transistor here which is taking this logic level here, the output of the AND gate, and inverting it. It's also acting like a level buffer as well to make sure that it goes right down to zero and right up to plus 5, or in this case it's actually plus 12. You'll notice the power supply here is actually a 12 volt supply inside of the Casio, and it's using the 12 volt rail for that. And then eventually we'll have our output, which is on the collector of this input pulse, and this is a balanced input as well. We need a balanced input really because the level signal from the sense wire is so small. It's only about 50 millivolts. It's not very big, very similar to the level you would get from, say, a dynamic microphone or something. So that's going to be susceptible to noise, in the background noise. The wires could be picking up other things, so we have to really feed this into a balanced input, and that's why we'll have a transformer input really. You can ignore this 1 mega ohm resistor to ground. That's just to keep Symetrix happy. It needs to see some sort of grounded net to somewhere on this side. If you lift this you get an error, but in the real circuit that's not there. And that's basically the whole circuit. What you can do is minimize this a little bit. We're only going to be using 5 volt rail. We could add logic chips if we wanted to, but to be honest we don't really need to, because this is going to be feeding an Arduino input pin on a port. It will automatically take care of the voltage level. Anything analog here should be enough to flip the state. I believe the inputs are actually Schmidt trigger inputs, so it should be able to flip the state, and we should be able to do this without any of this. Here's a simplified version. All this side of it is pretty much exactly the same. We haven't changed anything. The only thing I have done is change R3 value to 56k, but otherwise it's exactly the same. Where the difference is the output. So what we've done is simply wire the two collectors from the two transistors are now connected together with a single pull-up resistor If you remember, we had 2 pull-up resistors before. Now we've got a single pull-up resistor of 2.2k. So by doing that, these are basically open collector output. If you think about it, connected together, wired together. So if you think about it, that's either going to be a logic high if these are both off, or if any one of these switch on, if either one of these switch on, okay, and goes to ground, then you get a logic ground here. So that's our AND gate if you think about it. Now all I've done here as well is put a 74HC04 inverter on the output, and that's just for the purposes of looking at it in our simulation here to make sure that the logic levels do go to, you know, fully plus and fully minus, or close to +5 and 0 anyway. We don't really need this in the final design. As I said earlier, we can actually take this output from the 2 collectors and go straight to the input pin of the port on the Arduino. However, as I say, I've added this so we can do a simulation and have a look. So let's simulate this and press go. Alright, so okay, I'll just zoom in on this a bit so we can have a good look. I'll just zoom in again here. I hope you can actually see that. We've got a positive going pulse here. Okay, and that's from the positive edge trigger coming in from the pulse. And we've got another one here, also positive going here, positive logic, but that's detecting the negative pulse. So that's working fine, and you'll notice these levels are now 5-volt levels. So that's actually doing the job, and we don't really need the inverter. So yeah, if I take the inverter away, we'll just have a look. I'm just going to move this inverter and move this output pin. I'm now going to look at the output of the collector directly, and you'll notice it's not so digital anymore. We're probably not getting right at the rail. There you go. So let's zoom in on one of these. Okay, and we're down to like 3.25-ish volts here, 3.5, and up to about 3.7. But they are going down pretty much to 0. So you can see that that would probably be enough to flip the state of an input of a port pin. So basically we don't really need that inverter at all. You could put it in, I suppose. So this is going to be our sense amplifier, which is a modified version from the Casio AL-1000. Okay, so let's look at how we drive the core into a 1 or into a 0 state. And again, we're using Symetrix here. I've entered in a basic circuit. It looks more complicated than it actually is, and the reason for that is I'm using individual switches like S5 here, S1 here, and another 2 switches here, another 2 switches here, and another 2 switches here. So it kind of looks a little bit complicated, but in reality all these switches here and these inverters, you'll notice as well, is in one chip. There's a few chips that would do this job, H-bridge motor driver chips, and I'm probably going to use the L293 because basically I have some already. It looks worse than it is, but for the purposes of simulation this shows how it works. Let's have a look. Right in the center of this cross point here is our core. Imagine that's our ferrite ring just there, right in the center, so bear that in mind. And these cross point wires go through the core. Okay, we've got the X wire and we've got the Y wire. These wires are controlled by these switches in a H-bridge configuration. If you consider, say, just the top section to start off with, there's 4 of them, 1, 2, 3 and 4. Let's just look at the top one for now. You'll notice it's got a control signal. That's what this is. I'm using a little voltage source here to give us a 0 or a 1 control signal. So we'll only be setting that to 0 or 1 logic level. Yeah, so this signal comes in and this will control, first of all, S5 into its on state. So if a logic level of 1 coming in here would turn the switch on, and by turning the switch on you'll notice it connects up to the 5-volt rail. This is our power supply, 5 volts here. So we get 5 volts here, so the current flows through the switch down through this 10 ohm limiting resistor and then down to the bottom section through our current inline current sensors. into the simulator here so we can monitor the current in the lines. And there's another one for the X current as well. So we've got Y current and X current. Okay, so back to this. 5 volts here, or logic level here, will turn this switch on. You'll notice it goes through an inverter as well, which means turn this switch off. So this one will be open, this one will be closed, and that means we've got 5 volts coming straight through, current flowing through the limiting resistor, down the Y wire, and through the core, of course, down into this section here. If this is the Y bottom, if you like, the bottom of the Y wire. If this is also set to 5, this switch would be switched on, and you'll notice that the current, well, it actually can't flow because this is also at 5 volts here. This is all 5 volts here. So this would be at 5 volts here. This is all 5 volt rail here. So that's at 5 volts. And this switch would also be at 5 volts. So I think you can see that if both of these control input signals were high, you wouldn't get any current flowing through this wire at all. Now, the same applies if this is at 0, as shown here, and this end of the wire, Y bottom if you like, is also at 0, then the same applies, except this time both ends of the wire are connected to ground. And of course we have exactly the same circuit in the X direction as well. There's the X control signal here, left of wire, and then you've got the X control right on this side, and it's all exactly the same. So these 4 sections are actually identical except for the 2 limiting resistors here. Now these limiting resistors are here for a reason, and the purpose is to limit the current going through the driver wires through the core. If you didn't have those limiting resistors, obviously whatever current your power supply can drive would just burn these wires out and it would destroy your core memory. So but the other main reason, actually, it's not just a safety reason, but these are limiting current to the half current that we need to drive the cores. So each line is a half current in the Y direction and a half current in the X direction. And if you remember what we're talking about earlier, the sum of those gives us enough magnetism to flip the state of the core. So these 10 ohm resistors, if you do a little bit of quick Ohm's law from a 5 volt rail, then a bit of Ohm's law, it's 500 milliamps per line. So that'll give you 500 milliamps allowable, and that'll be 500 milliamps. Now we can simulate this and actually run this as if we made the circuit already. Here's our 5 volt power supply, and you'll notice all 4 control signals at the moment are set to a logic level low. That's 0, 0, over here 0 and 0. So from what we've just talked about here, what we just explained, it means there should be no current flowing through either wire. So let's try that and run it. Right, now hope you can see this, it's not very clear on the screen, but basically the X current is in green and the Y current is in red. They're both overlapping, actually. I can just make it out here. I hope you can see that. They're both at 0 amps. So this is our current scale here, 1 amp positive, 1 amp negative, and we are seeing 0. So that's exactly correct. Both lines are basically not passing any current. So let's turn the Y top wire to high, and I'm doing that here just by clicking this +5. That's now a +5 control signal coming in, and the bottom signal has to be the opposite, low, which it already is. So by setting Y top to high and Y bottom to low, we now have a current path. So that is the current path, basically from plus through the switch, through the resistor, and down to ground. So that should give us now 500 milliamps. Let's just see if that works. Let's try that. Right, okay. Now the X wire, which we haven't adjusted yet, is still at 0. There it is there in green. But now the Y current in the Y wire is now up here in red, and that is giving us, well, it's 490. There's probably resistance set for these switches internally, probably 100 milliohms or something like that. So yeah, anyway, but it's pretty much 500 milliamps. It's perfect. Now we've got current flowing through the wire. Let's put that one back to logic state 0, switch that line off. So now Y top and Y bottom are both logic 0. let's try the X out. So X left, let's put this high. Okay, so now that's a high, and this one is set to a low here, a 0. So now we should have current exactly the same, just, you know, just turned around 90 degrees. Now we should have current through the X wire. Let's try that. Let's have a look. Yeah, so now the Y current is at 0, that's in red, that's the Y current. But now the X current in green is now up to 500 milliamps, or very close to it, 490 milliamps. Close enough. So that worked. Now that would be a half current. That would be a half current. If you wanted to actually flip the state, remember they've got to be both on. So let's switch them both on. Okay. Now we've got a logic high to Y top, and we've got a logic high, okay, to X left. The right and the bottom wires are still at logic 0. So now we've got both wires passing current. Let's have a look at that. Now what you can see, or hope you can see, is that the current is actually passing in the same direction, because our X current in green and our Y current in red are both showing on the same line here at 490-ish milliamps. So that's absolutely correct. Both are now passing current. If we invert the current or reverse the current of one of the lines, let's say the X, let's put that down to 0, and let's put this over to +5. So now the logic, this is now a logic 1, this is now a logic 0, and let's run that again. Now what you can see now is a bit clearer, because now the X current is in green, which is minus 500 milliamps. So it's passing minus 500 milliamps, current's going the other way, and the Y current is up here in red, which is plus 500 milliamps. So that's absolutely perfect. So now we can actually pass currents in both the X and the Y wires in both directions, depending on the state of the input logic. This is the lash up that I've put together. It's a bit of a mess, but that doesn't matter. We're just on a fact-finding mission here, just to see if we can get the thing to work at all, and take some measurements, measure the access time, that sort of thing, of the cores. So I'll just briefly explain what's happening here. Obviously we've got the core storage device here. We'll have it wired up for just 1 bit. So there's a lot of it not being used. We're just testing 1 bit, which is X0, Y0, the very corner one there. And we've got, so these wires here are for the drive current for that bit. We've got our sense wires, that's these white wires coming out of here. That's the sense loop, which goes through all of the cores. The sense wire comes in here and goes to a transformer that I've had to wind. That basically gives us a balanced input, which works very well for noise rejection, because we've got reasonably low signals coming from the sense. It's only about 50 to 100 millivolt at its best. So there is a certain amount of noise. It's best to keep the whole thing balanced, which is why we do it this way. The output of this is a phase split, positive and negative phase split output with a center tap. That drives a couple of transistors here, and these transistors are basically detecting whether it's a positive or whether it's a negative pulse from the core, from the sense, because we need to detect both positive and negative pulses. So that's the sensing side coming back. The signal going to the core is done with this chip down here, which is an L293, and that is a H-bridge motor driver. It's actually designed to turn motors round, you know, left and turn them right, clockwise and anti-clockwise. So we're using that chip to actually drive the XY coordinate for the core. And we've got a little 5-volt regulator down here just for driving logic and the system. Everything's operating from 5 volts. Over here we'll have the Arduino development board. That's running a little bit of software, and what that's doing is supplying pulses to the H-bridge driver chip to give us our 1 and 0 test signals that we're running at the moment. And this is also connected through USB, which goes back to the PC, so we can actually do a bit of comms, and we can look at whether the core state flipped or not. And that's kind of it. That's our little test circuit, and that is giving us the output on the scope that we can look at right now. Okay, so here we are with the oscilloscope connected to the output of the sense amplifier, and the top trace here is basically the output being activated from a flipped state from the core. So we're either going from a 0 to a 1, or we're going from a 1 to a 0, and that gives us a sense pulse, if you like, a read bit, and this is the bit here going low and then coming high again when it's finished. This bottom trace is just a reference pulse, so we can see when the H bridge activated the core. So this is the beginning of the core being activated here, and it's just a short pulse, and as you can see there's a delay between the start of the pulse to the core and also to the delay to the read. And this gap here, using the cursor measurements here, it works out at about 500 nanoseconds. So that means that when we read a bit and look at the logic from the sense amplifier, we need to build in at least about 500 nanoseconds of delay before we actually sample whether it was a flipped state or not. And that's important. That's basically the access time of the core storage device. There's always a certain amount of delay, and you have to know what that is, and it probably changes from different core storage manufacturers depending on what type of ferrite they use and what size of ferrite ring it is. Once you know what this delay is, you can then sample the pulse from the amplifier, and that will tell you whether it's flipped state or whether it has not flipped state. Alright, so here we are at the PC, and I was looking around on the internet for inspiration to see if anybody else had done anything like this, and of course there are people that's done experiments. I found a couple of little pieces of code which inspired me to come up with this and make some alterations for my purposes for this video. I'll just run through the software briefly without going into too many details here. It's all not very complicated, to be honest. D2 we're going to be using as the chip enable to turn the L293 on and off. D3, D4 is Y bottom and Y top. This drives one of the lines through the core, in the Y direction. Then we have D5, D6, which is driving the X line through the core. And D8 is our sensing amplifier output, which comes to our input here. Alright, so that's just telling us how we're going to wire up the board to the driver and to the sense amp. Then we've got some definitions, which basically just sets up, gives us some characters here, which allows us to set up various pins on the ports. This code here is purely for reading from the serial port. We're going to be interacting with the Arduino over the serial comms port using the serial terminal, so we can interact with it. So this is just setting up buffers for the input characters. We're only using one. I've got it set to 8 as a safeguard, but we only use one character at a time. So in the setup code here, we've got some data direction registers. This sets D2 to D7 as outputs. This sets D8 as an input. That's all that's doing, setting up the direction. And this bit of code here is setting up the serial port. This is our main loop code here. So all I'm really doing is checking to see if we've received anything from the serial port. If there is, then do a bit of code here. If we have new data, we can interrogate that and see whether we've typed the letter R, which is our read command, or check whether we've pressed 1, which is our set core to a 1 logic state, or we've pressed 0, which means check for obviously a 0 state to the core. And we're doing some other stuff. We're sending a pulse when we get an R command. That means read the state of the core, and we've got a port bit pattern to write there, and we're also setting a bit for a scope trigger output. That means we can connect it to the scope and we can look at the actual the waveform synchronized to what the software is doing. So the scope trigger is purely for our purposes for monitoring on the oscilloscope. It's got nothing to do with writing to the core at all. Alright, this is all just reading of characters from the keyboard, from the serial port, so we can ignore that for now. Now this is the interesting part really. This is where things actually start to happen with our core storage. In this function here, sense pulse. So we're taking the input pin data that we've set up earlier, and we are doing all of this. Now I'll just explain what's going on here. So first of all, we're turning off the interrupts within the Arduino. That's because we really don't want anything to interrupt with the timing. This is what we would class as a critical timing section, where we don't really want any interruption. So we're trying to make a delay here of 500 nanoseconds. And if you remember when we looked at the scope when we did our tests earlier, that was indeed 500 nanoseconds from the start of the waveform to the sampling point from the output of the sensing amplifier. In our particular case, remember, it changes from core to core from different devices. Then you've got here set port D, which is the port that we're working with our pin configuration plus the enable pin. So that basically turns on the L293 with the pin configuration set at the same time. Okay, so we're ready to put current through the well, we are putting current through the L293H bridge. Then what we need to do is delay for exactly 500 nanoseconds. That's what these ASM NOP instructions do. You'll notice we've got 8 of these in a row, and ASM is assembler code. We're writing assembler code here. It's not C anymore, and that ensures that each one of these NOP instructions produces a 62.5 nanosecond delay. So every time you do an ASM, an assembler NOP if you like, the compiler knows what to do with that. That'll be 62.5 multiplied by 8, because we have 8 of these, which gives us our 500 nanosecond delay. Now after that delay, we want to actually sample the port pin which is connected to our sensing amplifier output. We are ANDing, that's the logical AND in the center there. We're doing a logical AND of that port with that pin to see whether it's been set or not. That tells us whether we had a flipped state in the core or not, and the return result is passed to res there as for result. Once we've done this critical section, once all that's completed, we can then return the interrupt state back on again. That just basically re-enables the interrupts so the Arduino can do its other service functions, anything else it likes after that. So we can start using standard library functions within the Arduino. This one here is a delay of microseconds, and it's not a precision delay anymore, and it doesn't need to be for our purposes here. It can be pretty loose. It doesn't matter if it's plus or minus or anything. After that 3 microsecond delay, we're kind of finished doing what we want to do. So then set the port back to 0. This turns off the current to the L293. Sets off the current going through the core wire. Delay on the end, another 3 microsecond, just for the sake of putting a delay at the end of it, in case we ever want to repeat this in a loop or anything. If we wanted to repeat it, we would need certain delays in here just to make sure that nothing's clashing, that we're not trying to like stop a waveform then start a waveform immediately after it, and then just return with the result. Okay, so this is really the heart of the code. We're setting the L293 into its current state to put current either forward or backward through either wire going through the core. That gives us control from the state of pins coming in here with the enable switched on. If we go back up here into the main loop, this is what's happening here. So if we received the character R through the serial port here, so we're checking for a key press of R. If that's the case, then we're going to use that pulse code that we just looked at earlier and set it into a read state. So we're going to set the lines to try and do a current read through the core to see if it's flipped state or not. Now you'll notice I've got a little comment here saying restore bit to previous state. Now if you remember what was said earlier, it's a destructive read when you read from a core store. So reading, actually you have to put current through it to flip its state to see what its previous state was. What this code is doing is putting that state back after a read. So we've done the read up here, and this is, well, if the result was 1, write a 1 back to the core. Simple. So if you read a 1, set it back to a 1. Else, if it's a 0, in other words, then write it back as a 0. So that's what this is doing. It's basically making sure that we put it back to its original state and that we don't lose the state of the data. And then we've got an output which basically sends the result, res, in a decimal format back to the serial terminal. Okay. Now these bits here are checking for a key press of 1. If it's a key press of 1, then we are sending a pulse. We're writing a 1 to the core. Very simple. And of course the other side, where if we've got a key press of 0, we are sending a pulse of write the 0 back to the core. So that they're just purely writes, and this is all read up here. And that's it. That's basically the whole software. The interesting bits, if you like, that actually writes to the core and reads from the core is all in this sense pulse function down here. Right, so what we can do is, let's just verify that. We'll do a little compile. That's actually compiling. I've got to scroll down so I can see the result there. Done compiling. Now uploading here. Wait for that. That says done uploading, so we are finished. So now what we can do is run the serial terminal, COM5 in this particular case, at 19,200 baud. Not that that matters, but just so you know we are connected. Now we've got our input terminal here. So finally, we're getting there. Let's see, after all that work, if we can write to the bit or read from the bit. So the first thing I want to do is the command R. I'll just zoom in. There you go. Let's try an R. What do we get? Okay, it's returned a 0 logic level. So far so good. So we've actually got data back from the core. Whoopee. Now, but does it work? Can we actually flip the state? So if I press 1, this will write a 1 to the core. Okay, I've done that now. Let's press R again. Now we'll read the core again. Yes. Now we get back a logic 1. Perfect. Now let's try writing a 0. Let's see if we can change that core to a logic 0. Okay, that's a 0 now. Okay, press R. We should get a 0. And we do. Yes. So there you go. Now the other thing we can demonstrate here is every time you press R, we should get the same result every time. So there's another 0. I'll just keep pressing R here. R, 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 R. And it's all zeros. You'll notice it's not forgetting the state. So let's try 1. Core's now set to a 1. Let's press R. We should get a 1. Yeah. Let's keep pressing R. 1, 1, 1, 1, 1. Yes. Perfect. And there you have it. So now we can write a 0 to the core, or we can write a 1 to the core, and it's not forgetting. We are correcting the state, restoring the previous to previous state there. So that's what that's doing, so we don't actually forget what we're doing. So yeah, pretty awesome. Now that, of course, it's only a single bit, and I know it's already been a pretty long video just to get to this point, and we've covered quite a lot of things on the way, you know, a few stories in there. So anyway, I hope at the end of all this you can see how it works, how you can actually write to a single bit and read back from it. Yeah, well, we got there, so that's a fantastic start. Unfortunately, it's only 1 bit. It's not very impressive. You can't do a lot with it at this point, but it really proves that the currents are correct, the half currents are correct, the sensing amplifier is working, a little bit of test code works, and all that kind of thing. So we've had a look on the scope, we've looked at the timing waveforms, and I hope you get an appreciation for how the technology worked all that time ago. And here we are doing exactly the same. So we've sort of brought it back to life. What I'm hoping to do in the next videos, of course, is to expand on this. We really need to get more data. We need to get at least a whole byte's worth of data, I would say, 8 bits worth. So then we can store ASCII characters. Better than that, try and get whole words of data, whole bytes or whole words of data. And maybe, I don't know, maybe we'll get to the point of writing hello world and saving that into the core storage. Who knows, whatever. Let us know in the comments if you want us to take this any further. It means a bit more circuitry, so would probably have to build a circuit, and you know, with a few more L293 chips on it, and or maybe I can come up with some other solution by looking around. Might get some inspiration off the internet, see how other people have done it, and maybe take that further. We'll see. But let us know in the comments if you want to go any further with this. It's already been a pretty long video. So anyway, I hope it's been of interest, and we'll leave it right there. So I want to thank you all for watching, and here's to the next time. Bye for now.